take a look at valid palindrome from the Grind 75 list of questions. A phrase is a palindrome if after converting all uppercase letters into lowercase letters and removing all non-alphanumeric characters, it reads the same forward and backward. Alphanumeric characters include letters and numbers. Given a string S, return true if it is a palindrome or false otherwise. Example, a man, a plan, a canal, Panama, true. The reason why this is true is because if we convert everything to lowercase and remove the spaces and remove the colon, this actually will be a palindrome, right? Because it converts to this, and you can see that yes, A is A, M is M, so on and so forth, which is why it's a palindrome. And this example, race a car, this is not a palindrome because the letters don't line up in the middle there. And for an empty space, this returns true because if you remove all of the non-alphanumeric characters, you get an empty string which reads the same forwards and backwards. All right, so the constraints are that we have to have at least one character in the string we get, up to a massive number basically. S only consists of printable ASCII characters. All right, so let's look at how we might solve this problem. Okay, so let's take a look at how we might solve the valid palindrome problem. So let's say we're given this string here. We have capital A, lowercase m, with a space that I'm representing with an underscore, capital M, colon A. So the first thing we need to do is actually sanitize this data. So we're going to write that down and figure out how we might sanitize the data and actually get it into a form that we can actually work with to determine if it's a palindrome. So the first thing we're going to do is lowercase it. So we're going to end up with M AM space M colon A. So everything's going to be lowercase. And then the second part we're going to do is we're going to remove all non-alphanumeric characters, which will result in a string called AMMA. And then from here, we can actually perform our algorithm. So what we're going to do with AMMA is look at the first character, and we're going to loop through half of the characters. We actually don't need to loop through the entire thing. So we're going to loop from left to right. So we're going to look at this A, and then we're going to say, okay, if the last index that is equivalent to this index, if that is the same character, we can keep going. As we can see, the A and the A are definitely good. So this is good, and then we're going to move on to the next character, and we're going to calculate that the mirror index, if you will, is also the same. So we're going to say yes, the M and the M are the same. Yes, we can say that this is valid. And so that's basically it as far as the algorithm goes. And so as far as time complexity, we are going to have a time complexity of O of n because we have to actually go through the entire string for the most part. And then as far as space complexity, it's going to be pretty much the same because we need to store the string as we modify it. And at most, it's going to take a linear space. All right, so let's take a look at the code and see how we might solve this. All right, so let's look at the code. And with many string problems, the thing that I like to start with is by converting it into, or converting the string rather, into an array of characters. And the way that you can do that is very simply by passing it into this array, and that'll give us an array of characters, which can make it a little bit easier when you're navigating through strings. However, one thing I want to do before we actually continue on here is convert it to lowercase. And there's actually something that we can do with strings itself. So we might say our string is equal to s dot, I believe it's lowercase, and that'll store the array as lowercase. So we're going to get rid of all the uppercase things. And now we're going to take this string that we have that's all lowercase and jam it in an array. So at this point, we've got a bunch of characters in an array, but we actually don't, we might have symbols or things like that that are not alphanumeric. So how might we do that? Well, simply we could do characters is equal to characters dot filter. I'm going to say 0, the character that we have dot is, I believe the function is letter, or is number. So we're saying, okay, we're going to filter out everything that's not a letter or a number. So at this point, we should have pretty sanitized data. Now we need to actually perform the validation to see if it's a palindrome. So I'm going to loop from left to right. So I'm going to go for I in 0 to less than, I'm going to say cars.count, but I'm actually going to divide it by 2 because we don't actually need to validate the whole thing. And now what we need to do is factor in the end index, right? So we know that if we're going from left to right, the character at the left is going to be cars of I, but what's the other one, right? If I need to get the index. So the actual end index, right? Or I'm going to call it the mirror index, is going to be equal to cars.count minus I. But this isn't quite right because this will actually give us something that's out of bounds. We actually need to subtract 1 on top of that. And I'm going to just condense this here. Maybe I'll put this as the first thing. So now what we need to do is go if cars of I, which is the character at the leftmost. So again, going back to this example, I had A, MMA. If cars of I, so we're going to start with I being at A, and then the mirror index is going to be cars.count minus I minus 1, which will give us the end A. If cars of I does not equal to cars of mirror index, then we're going to say return false. And if we can get through the whole string and we don't hit this if statement on line 11, then we know that we've actually got a valid palindrome. All right, as far as this problem is concerned anyways. Okay, so we submit this. You can see that the solution works to my satisfaction. All right, and hope you have a good day.